In this lecture, we're going to talk about circular economy and critical resources recovery, and you will see that to recover metals from many sources, we will need extractive metallurgy, and extractive metallurgy is my field of research, as I'm full professor at University of Lorraine and I work on hydrometallurgical processes. This lecture on circular economy and critical resources recovery addresses the principle of the circular economy before focusing on the unit operation implemented in recycling processes to recover valuable metals. These unit operations fall under the broader field of extractive metallurgy. In particular, this lecture will focus on the different operations used in hydrometallurgy, a branch of extractive metallurgy, as this technology enables the production of high-grade metals and high-grade purity salts, which are essential for producing material used in the energy and digital transitions. The circular economy is defined as a model of production and consumption which involves sharing, leasing, reusing, repairing, refurbishing, and recycling existing materials and products as long as possible. The circular economy can be a complex approach as it involves multiple stakeholders. Both materials and information flows pass through the entire value chain. The raw materials is first extracted from mine and transformed into products by manufacturer. The products are then transported to the distributors. The consumer buys the product, use them until their end of life. The spent objects are then collected. The product can be reused for a second life with or without reparation or sent to recycling plant to extract the raw material contained in the spent object. In particular, extractive metallurgy can be implemented to extract and valorize metals contained in these objects. These metals can then be reused in the value chain. Eco-design is particularly important in the circular economy as it facilitates the implementation of recycling processes. Products can be made from carefully selected materials to reduce the environmental and societal impact of their production, or designed in a way that makes recycling easier. The circular economy relies on three pillars. The first pillar is supply and economic actors. It relies on the use of supply of sustainable resources, whether renewable or non-renewable. Eco-design of goods and services plays a crucial role in reducing the impact of material production and product consumption. Additionally, organizing industries within a given territory helps optimize the value chain and minimize environmental impact. Another way to reduce the impact of daily activities is to promote the functional economy that favors services over ownerships. For example, leasing electric vehicle batteries instead of purchasing them can facilitate better collection and recycling management. Consumption, demand and behavior is another pillar that relies on responsible purchasing, proper use of products, and reliance on reuse and repair. The third pillar is waste management. This pillar should prioritize recycling and, if necessary, energy recovery, while responsible production and consumption help reduce waste generation. All these efforts aim to minimize ultimate waste, non-recoverable residual waste. The European passport for batteries is a good example of a new tool to promote the sustainable production of products. Here, the lithium-ion batteries. A battery passport is a document that stores relevant battery data throughout the entire battery life cycle, containing detailed information about batteries production, testing and recycling. More particularly, the passport will contain the following detailed information: origin of the material, source extraction method, and compliance with social and environmental rights with the supply chain. Greenhouse gas emission generated at each production stage, extraction and processing of materials up to the final assembly of the battery. Battery's performance, recycling compatibility. However, its implementation may be very challenging given the confidential information and the need to check the validity of this information. Extractive metallurgy is at the center of the processes for producing materials from primary resources, mining, and secondary resources, recycling. Metals can be extracted from mines, but also from mining residues, which now contain high amount of metals, sometimes at concentration higher than in ores. Likewise, metal extraction from spent materials is performed by extractive metallurgy. In this case, we talk about urban mining. Here is a battery value chain. Cobalt, nickel, manganese, and lithium are extracted from ores through mineral processing and hydrometallurgy, then converted into high-grade metal salts. These salts are used to produce cathode materials and cathode electrodes, which gigafactories use to manufacture batteries. This production process generates industrial scraps, effluent, and defective batteries, all of which must be processed to recover valuable metals. The recycling of industrial scraps and defective batteries follows the same unit operation as those used for lithium battery recycling. Once produced, these batteries are used until they reach the end of their life cycle. When spent batteries are collected, they are refurbished whenever possible. If refurbishment is not feasible, they are sent directly to the recycling plant where extractive metallurgical processes recover materials that can be reused to manufacture new electrodes for gigafactories. We are going to focus on the extractive metallurgy stage of the battery value chain. Raw materials or used objects are first processed through mineral processing, which enables the separation of different solid streams based on their physical properties. Initially, the materials are crushed, ground, and sieved. Among others, various separation techniques are then implemented, such as magnetic separation to distinguish magnetic from non-magnetic materials, gravimetric separation to classify materials by density, and flotation to separate material based on their hydrophobicity. By applying these unit operations, metals can be concentrated while undesirable elements are removed. This step is particularly important as it produces a material stream with a composition that facilitates the implementation of hydrometallurgical processes. Next, the concentrate can be processed using pyrometallurgy, which involves calcination, roasting, or smelting. Roasting can also be combined with hydrometallurgy as it facilitates subsequent hydrometallurgical processes. Hydrometallurgy is another route for processing the concentrate. It can treat smaller streams compared to pyrometallurgy while consuming less energy, and it produces high-grade materials. The first step in hydrometallurgy is dissolving the metals in an aqueous solution using acid or alkaline solution. Leaching efficiency can be enhanced by optimizing factors such as temperature, reagent concentration, and the solid-liquid ratio. Additionally, reactor design, propeller configuration, and increased reactor pressure all contribute to improve leaching efficiency. The goal is not only to maximize efficiency, but also to selectively dissolve the target metals. Therefore, the type of acid must be chosen carefully to reduce leaching cost and simplify subsequent operations. After leaching, the resulting aqueous solution generally contains both the target metals and some impurities. Therefore, it is necessary to either extract the valuable metals or remove the impurities while keeping the target metals in solution. This can be achieved through processes such as solvent extraction, cementation, precipitation, or crystallization. Precipitation involves adding a reagent that reacts with metals, either target metals or impurities, to form a new species with low solubility, causing it to precipitate as a solid. Solvent extraction consists of mixing the aqueous phase with an inimmiscible organic phase. Dispersing the organic phase into the aqueous phase, or vice versa, promotes the selective extraction of target metals from the aqueous phase into the organic phase. The metals are then recovered in a specific aqueous phase through back extraction using an appropriate aqueous solution. The choice of the organic phase, as well as extraction and back extraction conditions, is crucial for producing pure solution of the target metals. This solution can then undergo crystallization or precipitation to produce pure metal salts or electrolysis to obtain pure metals as final products. Here is an example of a typical hydrometallurgical process to recycle lithium-ion batteries. First, the concentrate, also called black mass, containing valuable metals is leached using sulfuric acid in the presence of hydrogen peroxide as a reductant. The resulting solution contains cobalt, nickel, manganese, and lithium, along with impurities such as traces of copper, aluminum, and iron. Copper can be removed either by solvent extraction or by precipitation, while iron and aluminum are eliminated through neutralization at pH around 3. Manganese is extracted by solvent extraction at pH 1.5 using a specific reagent such as Acorga or LAX extractant. Cobalt is extracted at pH 4.1 using Sinex 272, and nickel can be either precipitated at pH 9 as nickel hydroxide or extracted at pH 7 using Sinex 272. In this case, cobalt, nickel, and manganese can be crystallized as cobalt sulfate, nickel sulfate, and manganese sulfate respectively. At the end of this process, the aqueous solution containing lithium undergoes a precipitation step with sodium carbonate to produce lithium carbonate. All these salts, once purified to the required specification, can then be used to produce precursor for the synthesis of cathode materials for lithium-ion batteries. Thanks for learning with us.